Turn this off for a second. We have a belief about this. And the belief is that the Core Plus kids are not doing as well as the control group on the assessment when what? You guys, your claim before we left for the break was that the Core Plus kids, the control group's doing better. But only when, at least on this data, what was this data testing?
No.
When we said you can't use technology. So let's make a claim. This is without technology. Without technology. The claim is that the Core Plus kids, mu1, how are they going to compare to mu2 on average? On average, without technology? Be brave, you know it.
They're going to be worse.
They're going to be worse, so which sign's going to go there? Yes, there you go, less than. It's important to get that sign right. If you don't get that sign right, you get the complement of the p-value you're actually looking for, which is not where you want to be. Laura, ask me that question.
Wait, why is it less than?
Because your guys' claim is that these guys are doing better than these guys.
Oh, so it's
which means they're doing worse. You could also write it, if you want, Laura, you could write it as mu2 is greater than mu1. That means the same thing. But your belief, based on this, is that the control group's doing better, and the control group is what we define to be mu2. So mu2 has to be larger than mu1, no matter how you write it. Is that fair?
Yeah, but
So
say, what if we thought the opposite? Would we get the question wrong?
If you thought the opposite, let's see. If you thought the opposite, I could actually tell you, you wouldn't get it wrong, you'd be testing the wrong hypothesis. But I'll show you how the results will actually show you how to... Okay, I'm going to start that sentence again. Remember the question you just turned in on your take-home exam about the epileptic patients?
Sorry, not really.
That's okay. The epileptic patient said, we think seizure rates are higher during a full moon cycle.
Oh, great.
They presented their claim to the doctor tested it, and got a humongous p-value, which made him think, I think it's exactly the opposite of what they think. That would happen to you. If the claim actually holds water and you tested the opposite, you get a p-value of like 99.999 and then go, oh, if I just switch the sign and think the opposite of what I'm thinking, that actually is significant. That's what we'll actually do it. We'll actually do it here. After we do it this way, we'll go through it, switch the sign, you'll see what I'm talking about. Does that make sense?
Yeah.
Yeah, and that's why on your exams, first of all, I'll tell you what to test on your exam. I won't say this, what do you think? Who do you think's doing better? I'll say, test the claim that control groups are doing better than Core Plus. Good, Ashley's like, thank God. No, thank God, yeah, if you know what to test, you know what sign to put in. But Laura, in general, even if I gave you the claim, if you tested the claim you thought and it came back with a huge p-value, and I say huge, bigger than 95%, that means your alternate p-value would be less than 5%, which means you're like, oh, I should have tested that for significance. Does that make sense? You're asking like a 246 question versus a 244, which is great, because you're getting past what I would actually ask you to do in here, because I'm going to tell you which claim to test. Cool? All right, good. And then the null really isn't important. You can just slap an equal sign in there. It's not important anymore, only because I think we now know with certainty what has to be up there. It's the opposite of what's down here. That's why I always go to this first. And if you want, you can put the greater than or equals to up there versus just the equals. It's up to you guys. It's really not important. The claim you're testing is down here. Fantastic. Now all you got to do is generate these. And once we generate these, we know if we should believe our claim or not. So, let's do it. We only did a couple of these last time. Let me slap this. I guess I can just put it right here. Just put the screen. I just wonder why they put whiteboards in like this, instead of just having one big row of whiteboards with discrete pieces. I guess the fire alarm gets in the way. All right, data's in, yeah? Let's go. Stat, tests. Just like last time, 2 sample T. Stats or data? We actually have the data, one of those rare, beautiful cases. Now all you got to do is make sure that stuff is where it should be. And this is a fairly unique case because of the way we slapped our data in. What should list 1 be, do you think? I don't know what your guys look like compared to mine, but what do you think should be in list 1? What do you think? List 1 means data set 1. It's got to be L1. Good. How about list 2, which would be the data for the second group? Wouldn't it also be L1? Remember, we used L1 for all the data. So all the data is in the first list. All the data is in the first list. So list 1 is the Core Plus kids' data. List 2 is the control group's kids' data. The data itself is in list 1. So where do we indicate L2 and L3? Yes, in frequency. So frequency 1 is going to be the core plus kids frequencies. I think that was in L2, yeah? And then frequency 2 is going to be L3, because that's the control group's frequencies. Is that fair? Now, I think I have the right sign already highlighted, yeah? Yeah, because I want mu1 to be less than mu2. mu1 to be less than mu2. This pull thing, stupid. No, leave it on no all the time. It's dumb. Doesn't make any sense. It's not dumb. It's dumb. It's dumb practically. It's very smart statistically, mathematically. It's dumb practically. There's no reason to even think about it anymore. Calculator draw. I'm kind of a fan of drawing because you get exactly what you need and nothing more. Here comes the graph. I see some area down here. That's where it should be if we're going to have any area. It's a left-tailed test. The question is how much of it is there. See how small, see how long it takes it to graph. There's so much calculation going on right now.
Yours goes so much faster than mine.
I know, but still, compared to the z tables, the z tests fly through. All right, we got a test statistic of negative 2.2, which means it's t. And what that negative 2.2 again is a what? A number of what?
Standard deviation.
Good. Is that unusual? 2.2 standard deviations down from average? What do you think? If Josh is not, he's saying, yeah, I remember this from 243, that punishment I sat through in 243. If you're getting that far away from average, which is 0, something weird is happening. Something weird is happening. This assumes, right here, this part of the curve, what does that assume about the two groups of kids? It means that they're exactly the same. On this side over here, this would be the core plus kids doing better than the control groups. And this would be the core plus kids doing worse. Now, worse is a relative term. Is it significantly worse or just a little bit worse? That's what gets hard to tell from our box plots. Yeah, the box plot was shifted left, but is it so far left that it looks significant? This is the answer to that question. Yes, it is significant, yeah? Look at that p-value, 1.5%. That's significant. That means we do not believe we should be on the equals curve. I don't believe I should be on the curve that says they're doing the same because the data says otherwise. Now, Laura, back to your question. If you had tested the switched hypothesis, your p-value would be 0.9852. And you'd be like, ooh, that's big, but it's so big I think I should switch it around and test the other thing. Does that make sense? And that's what happened with the epileptic patients too as well. Cool? So the conclusion is that? What do you think? Try, if you can verbalize it now, when it comes to circling the correct conclusion on your exam, you'll ace it. So what do you think? What's the conclusion based on this data?
It appears that the control group tested better than the CP and P.
I love it! It appears the control group tested better. Love it. Could we be wrong?
Yes.
Of course we could be wrong. They could actually test worse. And we just missed it. What kind of error would we have made if that were the case?
Type 1.
It would be a type 1. It's always a type 1 potential when you have a small p-value. And what is the chance of that type 1 error?
5%.
It's 5%. Because that's what we're comparing the p-value to, is 5%. That's that max. Remember what I said to Laura, if you get a p-value over 95%, then you might want to switch your hypotheses around and test them the other way. And I'm basing that based on 5% confidence. Or 5% significance, not 5% confidence. Is that fair? You guys okay with that? Answer that question, Josh. Are you cool? Decent? How about if you let them use calculators? What if you let them use calculators? So let's retest with technology. With technology. Okay? Let's take all this out of here. We're going to leave the variables defined the same, I think. Test them with technology. What happens then?
So that was the L4 and L5, right?
That's where the L4 and L5 data lists are, yes? But again, although I would not torture you with forming your own hypothesis on an exam, based on this data, who's doing better or worse, or are they doing the same? What do you think? Analyze. Analyze your data, see what you think. Is either group doing better? You can't get significance from the raw data necessarily without running a significance test, but you can get a ballpark based on, how did you get your ballpark before? Before, when I asked you which group is doing better, what do we do to decide? Yeah, do it again. Lots of box plots up there. Just change the ones you've got. Change plot 1 to L1, L4, which would be, that would be control group, no, wrong, Core Plus with calculators. And change plot 2 to L1, L5, which would be control group with calculators. Cool? Let's take a look at them again. All right. So again, it's hard to measure significance from these box plots. But this guy is shifted to the right of this guy. And who's this up here? That's Core Plus. L1, L4. That's Core Plus with calculators. Now, what do you think? Are they doing better? Are they doing better? Yeah? Anybody say, no, they're so close, it's almost the same? That's a valid claim, too. Keller's going that route. He's like, I don't think they're doing that much better. They're doing better. The question is it statistically significantly better? And you can't figure that out based on this graph. I mean, yes, it's to the right. So technically speaking, on median, they're larger. On quartile, they're larger. On max, they're larger. On min, they're the same. But there's no test, there's no box plot test that I know of that we can do. But we can run this beautiful test of significance on two sample averages, and do it that way. We can do that. So, let's do it. First of all, let's come up, this is tight. Let's come up with a claim. We're going to put in H naught, KL is, we're the same. Totally fine. But a couple of you were nodding like, do you think the Core Plus kids are doing better? So what should the bottom hypothesis look like if we think now with technology, the Core Plus kids are doing better than the control groups? Yeah! Be that guy, wouldn't it? Because now we think that kids in Core Plus are doing better than the non-Core Plus kids. That's the claim we're going to test. And the best part is it's the same test in your TIs. You just got to go in and finagle the signs and the frequency lists. So, a 2-sample t-test. There's 3 things you have to change, and they're all pretty close to each other. You got to change the frequency lists to L4 and L5, and then switch the sign to greater than instead of less than. And don't forget Laura's awesome question from earlier when she asked about switching the sign inadvertently. The p-value, generally, if something is going on, the p-value will tell you if you picked the wrong way. Now, if the p-value is pretty close to, say, like 46% or 52% or something like that, then it doesn't matter anyway because there's no significance, either way, left or right. But if your p-value comes back at 0.99999, you might want to take a step back and go, holy crap, I think I just found something I wasn't expecting to find. Right? Like all of a sudden you discover that cocaine addicts live to be 120 years old, or something like that. Then you're like, holy crap, I wasn't expecting to find that. I was expecting them to die much sooner. But all of a sudden you found this ridiculous thing, and then you have to go figure out why. Okay. Just making that up, by the way. Just give you an example of something you would not be expecting to find in research study. Just, okay. No, you watch it, Dan. All right, here we go. What do you think? What do you think? Here comes your curve. If we have any area, it's going to be over here because it's right-tailed this time. And Cassie's not. I guess we have some. We got some area. That's 2 right there. We're at 2.02 as a statistic. About 2 standard deviations. About 2 standard deviations out. What's the p-value that it carries? Ish. Yep, about 2.3%. So what do we think's happening? What do we think? What's that tell us? I just found the casting.
What?
What? I'm not smiling.
It's...
I wasn't picking on you. I was saying, why are you smiling? I thought you had the answer. If you don't, that's totally fine. I won't pick on you.
No.
Okay, then I won't pick on you. What's going on? What's it tell us? Be brave. You all know this.
Core 1.
Eric, you're a saver. Every time you use the conclusion. Thank you. It looks like now Core Plus is doing better.
But how do you evaluate which one's better than the other since how you have calculators and no calculators?
Can we test that too? Assuming the assessment... Cassie's got a great question. Wait a minute now. Time out. We got core plus kids doing better with technology, and we got control group kids doing better without. How do we test them across the entire board? Got two answers for that. One is to run what's called an ANOVA test, which is the last thing we'll do in this class together. That's if you have 3 or more means. So you would test 4 different groups plus maybe even a 5th control group, and then test them all simultaneously at the same time. That's one way to do it. The other way to do it is maybe using the data we have. What can we do with the data we have? What do you think? What do you think? I'm not saying this would be the best thing to do because I'm not sure we would be allowed to do it because I'm not sure the assessment given to the with and without calculators was the same assessment. But assuming it was the same assessment, what can we do to test? What do you think, Tara? You think something over there? Go.
Well, could you like take the control group from the first set and then the CPM, whatever?
Yeah!
Like,
Why not do that? See? So take the best performing students in both groups, put them in, kind of like a what is that called? The bracket. You know? Like control group 1 without tech, core plus 1 with, they go to the next round and then fight off each other. We see who does it best. Why not? Let's try it. Let's try it. So let's graph it first. Now we're making a big assumption here, yes? YouTube world, making a big assumption. The assumption we're making is that the assessment that both groups used was identical and comparative. So let's make that assumption because it looks the scores at least are. So let's take a look at them first. So Tara, I love this idea by the way. Plot 1, let's leave plot 1 as L1, L4 because that's core plus kids with technology. So we're going to leave that graph up there. But let's change plot 2 to L1, L... It's going to be L1, L3, isn't it? Because isn't L1, L3 the control group kids without technology? Does that make sense? So switch that to L3 down there. Is that fair? Good, 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 good. Take a look at those. Zoom 9. Ooh. Whoops.
Whoa.
There might not be a difference. There might not be a difference. They look identical. Now, I say there might not be a difference. They look identical at 5 data points. The min, the max, the quartiles. There might be, and I can't tell this by not doing a more specific test. The data that's within these boxes is not necessarily uniformly spread through the boxes. So there might be clusters to one side or the other that I can't see. So that's where I think the test comes in handy. But right now, I don't know what to test.
Can you just do equals does not equals?
How about that? I was just going to recommend that, Rosie. Why not just do a does not equals test, a two-tailed test, and see if there's a difference. And then if there's a difference, we can go back and reevaluate. I think that's a great idea, Rosie. So now we're going to do, what is this? This is final game. Final's going to be core plus with tech versus control without. Final match. This is Timbers and Real Salt Lake on Sunday. We lost last week. We're going to crush it this week up at Joe Gwen. So, we're going to go equals, does not equal, and see if we see anything. Now this doesn't give me hope that we're going to see anything. Right here. Tara, this was your idea, right? This is fantastic. I love this idea. Seeing the cream of the crop for both and see how they compare. Because this could also silence criticism of using technology in classrooms. How do they know to learn math if they're using technology? I don't know. I think they are. I think they are. I mean, based on assessment, I think you guys are picking up math. This doesn't mean that it's doing any thinking for you. It's just doing the heavy lifting for you. All right, let's go in. Still 2 samples t-test. I think all we got to do is change freak 2 to L3. I think that's it. And the sign. So it does not equal. Huge p-value. Well, that's not very convincing anything's going on differently with a huge p-value, yes? L4, L3 does not equals. Look for area. There's a lot of it. A lot of area. But once we see the test statistic, this is a perfect example of, is it positive or negative? It's positive. It's a positive 0.4652, yeah? You got a negative on yours, Wilson? Did you put L3, L4, or L4, L3? And that's okay, don't worry about it. Here's the way it is. This tells me that because I subtracted core plus minus traditional. That's the way this was constructed, because I put my core plus in L1 and my traditional in L2. Core plus minus traditional yielded a positive average overall. So, core plus was doing better on average, but not, say it again, loud. Louder. Say it, Kayla, you know it. Significantly better. Better, but so close to zero as if to say there's no difference, there's no real difference. That could have been easily explained by random fluctuations in the sample. The sampling error could have eaten up all of that. Because be brave, my friend, you know it. And that's why you got negative, Rosie, because you're subtracted the other way. You did traditional minus core plus, which give the same value but negative. So the box plots kind of gave us a good idea, like nothing's really going on, they're doing it about the same. Which is interesting, because then critics of core plus will come back and say, well, we'll just keep doing the way we're always doing it because you're not increasing scores at all. And so proponents of core plus says, yes, but if we can increase the use of technology in classrooms, are we preparing students better for the 21st century? And then the debate continues until you get more data. Now, could we make this significant? Even though it's a small difference, can we make this significant? Not with this sample, not with this study. But could this be made significant in the future? Possibly. Go get a larger sample. You go get a larger sample, and all of a sudden that might be able to become significant. Let me see if I can illustrate for you here. I think I can maintain everything. So let me run one thing real quick for you to show you what I'm talking about. I'm going to do a calculate versus. There's a calculation of the versus. This is the calculate screen versus the draw screen. So you can see core plus kids on average have an average of 38.8. Traditional have 37.6. Not a big difference, right? Not a big difference. Not a big difference at all. You got the standard deviations down here. There they are, pretty wide standard deviations, right? Degrees of freedom, please don't worry yourselves about that. You might remember that phrase from last time. That's the T-curve changes as that number changes. The degrees of freedom is tied to your sample size in a very, very bizarre way. Don't trouble yourselves about it. But if I go in here, and let's just say, I'm going to make this completely fictitious. I'm going to multiply all the frequencies by 10. So L4 and L3 we're multiply by 10, that's what we're testing right now. So we'll make this 20, 60, 30, 40, 70, 60, 70, 40, 50, 60, 10, and we're done. 50, 20. So what I'm kind of fictitiously creating here is what?
Bigger sample size.
A bigger sample size, and also what? That's very good, Cassie. A larger sample size, and also what? So I can illustrate here for you guys.
Really quickly, on the conclusion for this one, it would be, it appears that it does not.
Say it again.
On the conclusion for this one, before you multiply.
Yes.
It would just be,
It appears the core plus kids are doing, excuse me, sorry, yes, it appears there's no difference at all between core plus and good. Thank you, Rosie, thank you. Now, Dina, when I said, what did I just do? Now, if you look at this screen, a couple things look exactly the same, don't they? The averages of the tests are exactly the same as they were before. Still 38.8, still 37.5. The reason is because I didn't skew anything, I just multiplied everything by 10. There's 10 times as many kids getting the same, but it's always 10 times as many, so the average stays exactly the same. But the p-value went way down, didn't it? Because if you then take a look at this, draw, you're still going to get too much area to believe there's a difference. But look where the area stops. That's because the test statistic is now much, much, much more to, actually it's to this side. It's much, much more to this side. 1.5 standard deviations versus a half of a standard deviation. Now here's where the TI sucks. The TI should have changed the shape of that curve. It should have changed the shape of that curve, because you're still at the exact same place statistically that you were before, but that place is a different number of standard deviations away from average now because your sample size is way up. So my question is, or my statement was, can we eventually believe that a difference of less than a point in test score is significant? And the answer always is yes, if you can get enough data to support it. And that's kind of tied back to the question you started the day with today, Rosie, which was that power calculation. How big of a sample would you need if you expected this much of a difference? That's what that prompt kind of walks you through. Cool? Yeah. So this is where it's all starting to tie together now. So darn, I'm afraid there's no difference. I apologize. Bummer. That's okay though. The debate continues. Maybe there is a difference and we just haven't measured it yet. That's all. That's all. I read it. It was a great quote from Albert Einstein. I'm not sure if it's Albert Einstein. It was attributed to him. That's who I saw it. Not everything that counts can be counted, and not everything that can be counted counts. And I remember reading that the first time, being like, okay, he's pulling a St. Francis de Sales thing here. He's talking around circles. But then I realized what he's talking about. I mentioned earlier today, you can't measure the spark of mathematical interest in students. But that doesn't mean it doesn't count, just because you can't measure something. And we have this discussion very often as educators, like, how do you know if students are getting it? And my contention is you never will. I assess you as many ways as I can. I try to get as many incomplete pieces of data as I possibly can, and I hope that I can put that kind of that light, that spark, and partially. If I keep flint and stealing at you, maybe one of those sparks will catch, or at least make sense to you. So, I love that quote. It's such a wonderful thing. But there are some things that can be counted, like we're looking at right now. All right, so I think we've exhausted Core Plus. Let's start and stop this again.